it's a really great pleasure for me to be invited here as a materials person to this neuromorphic conference. So as you can see in our institute, at the Forschungszentrum Jülich, we are working a lot on materials and phenomena, and we are trying to develop based on these devices and technology and have a deep knowledge on the basics on this. So in cooperation with our partners at the Forschungszentrum Jülich, we are also striving to use our device technology for memristive neuromorphic hardware. So you might have seen this type of memristive devices, which we call valence change memory. And in the yesterday's presentation, you have seen that the maturity of this type of memristive devices, which are based on the movement of ions, already entered the embedded market. So, but there's much more about memristive devices than using it as a usual non-volatile memory. So this is a kind of collection I made together with John Paul a few years ago. So there are a lot of different possible application of memristive devices based on the analog operation mode and the very dynamic properties of the devices in terms of using in terms of neural network, but also very bio-inspired approaches like spiking neural networks. So there are a lot of possibilities, but I will talk about today will be two different things, which we are doing with memristive crossbar arrays in our institute. So in the first talk, I will talk about the CMOS integration and interaction and crossbar arrays. And in the second part, I will talk about a little bit more uncommon type of behavior of memristive crossbar arrays, which might inspire you perhaps to implement some learning routes in the future. So let's start with the memristive crossbar arrays. So the background you might know, there are a lot of possibilities how to make use of memristive crossbar arrays for applications. So there's the core operation mode, the matrix vector, vector multiplication, which is a very common procedure, which is usually consuming a lot of energy. So we can do this in these crossbar arrays in a single step. But there are also other possibilities to use them for neural networks or for associate memories. And this is what we are doing in the team in the Forschungszentrum Jülich in our neurotech project with our partners from the circuit design, from neuromorphic hardware and software. And we are aiming to put these crossbar arrays together on a chip with a processor and network on chip to finally have a digital support on the chip. So, but let me start where we come into play, our competence. So this is where we spent a lot of efforts in the group of Susanne Hoffmann-Eifert. She strongly pushed this topic to integrate our memristive devices on CMOS chips, which were developed in the group of Stefan von Waasen in the Forschungszentrum Jülich, and then taped out, and now we received these multi-purpose chips and put our memristors on top. So in particular, this was quite complex for the TSMC 28 nanometer technology because it goes along with copper. This causes a lot of problems or challenges in our institute. So, but we finally managed to do this and have now these nice memristive devices on top of the CMOS chips. As you can see here, our main material route here for the TSMC chip is the tantalum oxide system. But some years ago, we already started to do the CMOS integration on the X-FAB technology in a 180 nanometer node. And I will now mostly talk in the first part, about our experience on this X-FAB chip. So when we have in all these crossbar arrays, we have 1T, 1R cells, namely the transistor in these crossbar arrays acts on the one hand as a selector, on the second hand as a current compliance for the devices which show this, again, some technical problem. So which again, yeah. Oh, that's good. That's good. Yeah. Okay. So as you can see, the memristive devices, this filamentary process goes along with strong thermal acceleration of the switching process, and as a result of this, we have this self-heating process in the devices, and this has to be limited by a current compliance, and the transistors act as a current compliance in the 1T1R crossbar arrays. So, but as you can see here, the size and the dynamics of the transistors have a strong impact on also the electrical properties of the memristor. So therefore, we spent efforts in investigating transistors in different sizes and have a look on the distribution of the voltages and the dynamics of the system depending on the size of the transistor. So what you can see here is that we apply the voltage, the ground on the side of the transistor, the voltage on top, the bias on the memristor, and now we have a series connection of the transistor and the memristor. And now the question is, when we apply a voltage to the system, how is the voltage divided between the transistor and the memristor? So therefore, what we did is we measured the characteristics of the transistor and then calculated back by assuming a series resistor model calculated back on the real voltage on the memristor itself. So as you can see here already from the current voltage curves of the memristors with the applied voltage, you see that for different sizes of the transistors, you see in one case it really acts only as a current compliance, as a current limiter for the large systems. But if you go to smaller transistors, you see that you also have some strong deformation of the current voltage curves due to the transistor. And this is related to the different operation points of the transistors. So yeah, in order to investigate the operation mode we would like to do with the transistors is to work in a multi-level switching mode. So therefore, we used a set programming algorithm to apply to switch the memristor into different resistive states. So what you can see here is that we have some conditioning at the beginning to set the transistor in a defined state, and then we apply certain voltage pulses in a read-verify algorithm, and then we increase incrementally the gate voltage at the transistor. And since it acts as a current compliance, you can see that you incrementally also increase the current in the transistor, namely you program the memristor, into different currents and into different resistance states by this procedure. Now have a look on how the voltage during the programming with different conditions and different transistors evolves during while we increase the gate voltage. So what you can see here is for two different applied voltage pulses in this algorithm, you see here the increase of the read current and the increase of the current during the writing with the gate voltage. And we now calculated this the voltage drop during this procedure, the voltage drop and the transistor. This is the red curve, and the blue curve is the transistor voltage. So, and what's interesting to see here is that irrespective of the voltage you apply, you get about always the same set voltage and the transistor, namely 0.7 volt, irrespective on the applied voltage to the 1T1R structure. That means that there's some kind of intrinsic switching voltage of the transistor, and the remaining voltage drop occurs in the memristor, and the remaining voltage drop drops at the transistor. So that means if you apply high voltages to your system, that causes some more stress to the transistor. On the other hand, if you take the switching pulse voltage too small, you might run into the problem that the voltage drop at the transistor at the memristor is not sufficient. So there's a complex interplay here between the memristor and the transistor, and this is finally some kind of nice overview which shows for the two different voltage pulses the operation point of the transistor for low voltage and high voltage for three different sizes of the transistors. And what you can see here is that if you would like to operate really in the saturation regime of the transistor, you have to take the large transistors. If you go to the smaller transistors, you shift, depending on the voltage you apply, you shift into the linear regime of the transistor, and here even in the transition regime, and here in the really linear regime of the transistor, which is not optimum for the work as a current compliance, and also it can be assumed that this is not a reliable way to adjust the resistance values of the memristor with the transistor. So this is it's a kind of what we learned from this is really you have to adapt properly your transistor to the memristor you are using, as well as to the operation regime. So it's not a plug and play taking the transistor and creating 1T1R structure. So based on this knowledge of how we operate this, I show you one preliminary example on our CMOS chips, where we demonstrate in a 4x4 crossbar array vector matrix multiplication, but we have much larger arrays on our chips, and we will proceed with doing more complex operations of our chips in the future. So now with this, I would like to move to the second topic, which is very strongly related to the dynamics of our transistors, of our memristors. So what you might know is the operation of these devices is based on the thermal acceleration of ions in the system, and during the set and the reset pulse, we get a strong Joule heating inside these devices. So the whole dynamics of the devices over the years, Stefan Menzel and his team have developed a couple of very powerful simulation models, which are accessible by this web page. These are the JARD models, and there are physical models, continuous models, but also compact models, which can be combined, can be used for circuit design. So now these models have been used to simulate what goes on in crossbar arrays, where we become very close with the memristors, and the Joule heating taking place during the switching process of one selected memristor might influence the surrounding memristors. So this is the work of Daniel Schön and Stefan's group, who simulated then the thermal distribution and the result on the resistance levels and the switching properties. So here what he considered is the heat transfer in the arrays and its impact on the electrical conductivity, and in particular the oxygen vacancy concentration at the most important active interface. So and what you can see here in this matrix of different different memristors inside a crossbar array. You see this is the selected memristor, which has 900 degree Kelvin in the set process, but you see that also the surrounding memristive devices are becoming quite hot. So additional to the heat transport via the electrodes from the Joule heating inside the memristor, there's also some additional heat coming from the heat in the lines of the crossbar arrays. So important here, and if we consider a crossbar array and the density of the crossbar array, is what is here the key parameter is the so-called alpha value, which describes here the relationship of the heat from the selected one to the unselected ones. And here you can see the calculations for different spacings, and for different distances, different positions of the memristor compared to the selected one. And what you can see here, for large spacings, this does not play a significant role. So if you have spacings in the order of 800 nanometers, this is really not important. It becomes important here below 200 nanometer distance in the crossbar array, where you can have considerable crosstalk among the devices. So here are some simulations of the temperature and the oxygen vacancy concentration of two memristors next to the selected memristor, which are half selected. And you can see here that you have a considerable, during the pulsing of the selected memristors, you get considerable heating during these pulses in the two surrounding memristors, and a considerable increase of the oxygen vacancy concentration in the devices. So, but besides this, in order to understand the full interaction in arrays, besides the crosstalk, you also have to consider thermal accumulation in one memristor itself. So what is shown here is that you see that you get Joule heating during the pulses, and then during the waiting point to the next pulse, you get some cooling, and then again heating. And then if the pulses are very close and very fast after each other, you will get the accumulation of heat, because it will not completely cool down over the time. So this results in this transient behavior here of the memristors. And if you have a look on the set process, you see that for pulses with a distance of 20 nanoseconds, the pulses are more or less independent in terms of the temperature increase. So it always has the time to cool down before the next pulse is coming. But then if you move into a 8 nanosecond regime, they start to accumulate, and here it's very pronounced that you're never cooling down before the next pulse is coming. So it means this is for the set process. For the reset process, the influence is much more pronounced on the switching behavior. You see here, for the very far away pulses, you're not even changing the resistance, so the device is not switching at all. And here you see, if you become very close with the pulse distance in time, you can switch the device, you can reset the device. With the same pulse height, then the others which have not been switched. So we observe, based on this, a frequency-dependent switching due to the thermal accumulation in the memristive devices. So now if we put all things together, the accumulation effect as well as the crosstalk, you can see that the temperature coming from the Joule heating can be regarded as the second state variable of the memristor transferred by the surrounding cells. So here you see there's a long time, this is the selected memristor, and these are pulses coming before So this is the temperature increase coming from the surrounding memristor. And here the small peak coming afterwards come from the selection and the pulse which is put on the memristor itself. So if you move closer in time, you see that there's a considerable overlap of the pulse coming from the surrounding and from the self-heating in the memristor. And here, as a result, if you are very short in time, the accumulation effect plays a very prominent role. So the temperature coming from the surrounding is strongly accumulating with the temperature coming from the pulse on the selected memristor itself, and then you get this very strong change of the device of the oxygen vacancy concentration and the resistance in the device. So this is could be a nice scenario here to work with the surrounding and get due to the thermal effects, some spatial temporal correlation in memristive crossbar arrays, which might be useful to implement some certain type of algorithm and learning rules. So now let me come to the summary of my presentation. In the first part, I talked about our CMOS co-integration efforts in Jülich on different types of CMOS chips. We investigated in detail the complex interplay between the transistor and the memristor, and you have to carefully think about these interplay when you start to build and measure 1T1R crossbar arrays. And finally, we were able to demonstrate a vector matrix multiplication on our CMOS chips. In the second part, I talk about thermal coupling in memristor arrays. So there are two effects. There's first the thermal crossbar in very dense array, and the second effect is the self-heating in a single memristor and the resulting thermal accumulation for very short coming pulse. And finally, putting all these things together, we have a nice playground of getting spatial temporal thermal effects in memristor crossbar arrays, which might be interesting for future implementation of biological learning routes. So finally, I would like to thank my team members in Jülich, the funding agencies and the cooperation partners on campus, and I will be happy to answer your questions.